Okay, we'll talk about controllability of control systems. What does it mean in words? It means you can drive every state variable. Remember, we're talking state space now. So this vector X, every element of that vector can reach a certain objective in finite time if you give it the right kind of input. And how can we tell if it's observable? Without derivation, in general, you form this controllability matrix. All you need are the A and B, so we sometimes call it AB controllable. Form this matrix and see if it has a rank of n, where n is the number of states in the state vector, and the number of state variables in the state vector X. In my course, we limit ourselves to 2x2 matrices, which just relieves us of some more tedious or a little bit more matrix arithmetic otherwise would have to do. So this becomes much more simple. If we form this observability matrix S, now it's only going to be two columns rather, B and product AB. This determinant is not equal 0, then it is control. There are alternate tests if it's in canonical format. You can put it in control canonical form and it is controllable. And if it's in diagonal canonical form and all rows of B are not 0, then it is controllable. We'll do examples of these later. Here's the first one. Here's our state space representation. All we need is A and B. So B is 1, 1. We're going to need AB. Here's A times B. Do that matrix multiply. It's 1 minus 9. Form this matrix. B is 1, 1. AB is 1 minus 9. That determinant is minus 9 minus 1. Or minus 10. That's not 0. So this system is controllable. Now, the other thing, observability. In words, a system is completely observable if every state variable affects some of the outputs. So we can observe all the state variables just from knowing inputs and outputs of the system. It's kind of a long-winded definition. Think about it. You can determine all the state variables if you know the input and outputs of the system. Again, we have what we call an observability matrix V that's formed this way. So we can say it only involves the matrices A and C of the state space model. Anyway, this observability matrix must have rank n, and is the number of states in the state vector. And if we limit ourselves to 2x2 matrices, it's observable if this determinant is not equal 0. C and the product CA. So the top row is C, the second row is the product CA. Alternate test if it's in control canonical format. You can put it in observer canonical format, then it is observable. Or if A is in diagonal canonical form, and all columns of C are not 0, then it is observable. Here's an example of the observability matrix. Take this, is this the same example? I'm not sure. We're going to need to find this product CA. Here is C, here is A. So do this product, I get 2, 0, 1. So C, this upper row, is that 1, 0. That's what CA is. Excuse me. Here's what C is, 1, 0. In the bottom row is CA, that's 0, 1. That determinant is 1. That's not 0, so this guy is controllable. Let's do this guy all the way through. Here's the state space for the observability matrix S, we need to do this matrix multiply. A times B. 3 plus 2, 1 plus 4, so that is 5, 5. B is the first column. There's B. AB is the second column. 5, 5. 5 minus 5, that's 0. This guy is not observable, or not controllable. Let's see if he's observable. We need to do this matrix multiply. C times A. Here is C, here is A. Do that matrix multiply, you get 3, 2. So the top row is 1, 0. Bottom row is 3, 2. That determinant is 2, which is not 0, so it is observable. This guy is observable, but not controllable. Here's some of the other examples that are in diagonal canonical form. This guy, it's all diagonal. Every element in this B matrix is non-zero, so he is controllable. This guy's in diagonal form. The A is in diagonal form. We've got a 0 in B. He is not controllable. Again, A is diagonal, in all these cases. Here, C is all non-zero, so it is observable. This C has a 0 in it, so it is not observable. So you look at B for controllability and C for observability. And if you can put it in control canonical form, it is controllable. And if you can put it in observer canonical form, it is observable. Let's look at the example where it was, let's see, not controllable, but it was observable. Let's find this guy's transfer function. We had a way to do that before. We had to do this SI minus A inverse. I won't go through this matrix arithmetic. And you had this formula for writing the transfer function. Again, this is in previous videos. You go through all that matrix arithmetic, you get this. You see that there is a pole and a 0 that cancel. Let's see what happens. So here's our transfer function, but we won't let them cancel. So we have this, and we can put, remember from this format, we can put it in either control canonical form or observer canonical form. There's formulas for that, or you look it up on a formula sheet. In control canonical form, it's this. Well, first we put it in control canonical form, so it's controllable. But if you actually check the controllability, or okay, we know it's controllable. Let's check its observability. We'll go through the matrix arithmetic in this case, go through it, and you find that it is not observable. So you could make it controllable, but it wasn't observable. Remember, we had a pole and 0 cancel. We'll do the same thing, but find the observer canonical form, so it is observable. Now let's look at the controllability matrix, and its determinant, you get a 0, so it's not controllable. So you could make it observable, but not controllable. You have your choice if you, by what canonical format you use, but it can't be both, and that's because you had a pole and a 0 cancel. That's the end of controllability and observability. The next subject is state feedback. It's going to be another future video.